Welcome to a webcast produced by the Learning Enhancement team based in the Dean of Students office at the University of East Anglia. This webcast is part of the Steps into Algebra series and concerns the laws of indices. This guide describes how to work with and manipulate the laws of indices in mathematics. What are indices? Indices usually appear in mathematics as a numerical superscript after a number or variable and are also known as powers or exponents. The word indices is the plural of index. The most common use of an index is to represent multiplication of a variable or number by itself a number of times. They can also be used to describe reciprocals and roots. Some examples are 10 to the power 3, x to the power minus 1, and p to the power a half. The index can be any positive or negative number, or 0. Different types of numerical indices represent different types of mathematics, and this guide looks at each of them in detail. A number or variable with an index is called the base, so 10 is the base in 10 to the power 3, and x is the base in x to the power minus 1. Positive whole number indices. Positive whole number indices represent the number of times a variable or number is multiplied by itself. It is important not to confuse this with addition, as this leads to very common errors. From now on, the notation dot will be used for multiplication instead of x, to stop any confusion between multiplication and the variable x. Let's look at an example. What is x times x times x times x expressed in index form? The variable x is multiplied by itself 4 times, and so the index form is x to the power 4. You can say x to the power 4 or simply x to the 4. Try not to say x4, as this can lead to confusion. You can see why index notation is beneficial, as it saves time and space in writing mathematics. Think about what x to the 25 represents. Do not confuse x to the power 4 with 4 lots of x, as this is x plus x plus x plus x, which equals 4x, something completely different. Let's look at a numerical example. Calculate 3 to the power 2 and 5 to the power 3. 3 to the power 2 equals 3 times 3, which is 9. An index of 2 has a special name, and 3 to the power 2 is said 3 squared. You can think of 3 squared as the area of a square with a side length of 3. 5 to the power 3 equals 5 times 5 times 5, which equals 125. The index of 3 also has a special name, and 5 to the power 3 is said 5 cubed. 5 cubed can be thought of as the volume of a cube with side length of 5. If you are comfortable with the above examples, you can deduce the first law of indices. Example: what is x squared times x cubed written as a single index? If you write out x squared and x cubed in full, you find that x squared times x cubed equals x times x, which is x squared, multiplied by x times x times x, which is x cubed. The brackets have been introduced to help you see what has happened, but really there is no need for them, as multiplication can be carried out in any order. So really, x squared times x cubed equals x times x times x times x times x, which equals x to the power 5. Similarly, x squared times x squared equals x times x times x times x, which equals x to the 4, and x squared times x to the 4 equals x times x times x times x times x times x, which equals x to the 6. Can you see a pattern emerging? To get the index of the answer, you add the indices in the question. Mathematically, this can be written as x to the power m times x to the power n equals x to the power m plus n, which is the first law of indices. Importantly, x is the base throughout, and this must be the case for you to use the first law of indices. So, for example, p cubed times p to the 8 equals p to the power 3 plus 8, which equals p to the power 11. However, p cubed times q to the 8 cannot be simplified using the law, as we have different bases, p and q. The first law of indices is true when m and n are any number, either positive, negative, or a fraction. You can deduce an important fact about indices from the first law. Think about each of the following: x times x squared and x times x to the 4. By writing out the mathematics in full, can you see that x times x squared is equal to x cubed and x times x to the 4 is equal to x to the 5? The only way that the first law of indices remains true is if that x equals x to the power 1. So, x times x squared equals x to the power 1 times x squared, which equals, from the first law of indices, x to the power 1 plus 2, which equals x to the power 3, or simply x cubed. And x times x to the 4 equals x to the 1 times x to the 4, which equals, from the first law of indices, x to the power 1 plus 4, which equals x to the power 5. It is true that x equals x to the power 1, which can be thought of as anything to the power 1 is itself. This is really useful when manipulating indices. Negative whole number indices. You have seen how the first law of indices can be deduced from multiplying variables together. Another law can be found from the division of variables. If you find the following difficult, read the study guide, Cancelling Down Fractions. Let's look at an example. Simplify x to the power 5 divided by x to the power 3. In algebra, you will rarely see the symbol divide, as division is almost always implied by writing an expression as a fraction. So, doing this, x to the power 5 divided by x to the power 3 is, as x to the power 5 is the numerator, and x to the power 3 is the denominator. And so, cancelling down, you get x times x divided by 1, which is x squared. And so, x to the power 5 divided by x to the power 3 is x squared. Or, x to the power 5 divided by x to the power 3 equals x squared. Again, can you see a pattern? So, when multiplying variables you add the indices, and when dividing variables you subtract the indices. So, in general, x to the power m divided by x to the power n equals x to the power m minus n, which is the second law of indices. Again, the bases must be the same for this to work. You can deduce two useful facts from this law. Let's think about x cubed divided by x cubed. Written out in full, you find that x cubed divided by x cubed is the same as x times x times x divided by x times x times x. After cancelling down, you get 1 divided by 1, which is simply 1. Alternatively, using the law, x to the power 3 divided by x to the power 3 equals x to the power 3 minus 3, which equals x to the power 0, which implies that x to the power 0 equals 1. This is true for any x except 0, in order for the laws of indices to hold. This equation says that anything to the power 0 is equal to 1. This is extremely useful in algebra. What happens if the index associated with the denominator is larger than that associated with the numerator? Think about x to the power 3 divided by x to the power 5. Writing out in full, you find that x to the power 3 divided by x to the power 5 is x times x times x divided by x times x times x times x times x. After cancelling down, you have 1 over x times x, which is 1 over x squared. Alternatively, using the second law, x to the power 3 divided by x to the power 5 equals x to the power minus 2. This example implies that 1 over x to the power 2 is equal to x to the power minus 2. In general, 1 over x to the power n is equal to x to the power minus n, where x can be any number except for 0, and allows you to express reciprocals in terms of indices. In other words, reciprocals are represented by indices of opposite sign. Let's do a numerical example. Calculate 4 to the power 3 divided by 4 to the power 5. Using the second law, 4 to the power 3 divided by 4 to the power 5 equals 4 to the power 3 subtract 5, which equals 4 to the power minus 2. You can use the reciprocal law with n equals 2 to calculate that. 4 to the power minus 2 equals 1 over 4 to the power 2, which equals 1 over 16. You can also use the reciprocal law to show that the first and second laws of indices are connected to each other. In fact, the second law is a reinterpretation of the first. Start by writing the second law as a product of two fractions. The second law is x to the power m divided by x to the power n, which equals x to the power m divided by 1 multiplied by 1 over x to the power n, which equals x to the power m multiplied by 1 over x to the n. Now, rewriting the reciprocal 1 over x to the n as x to the minus n, you find that x to the power m multiplied by 1 over x to the n equals x to the power m multiplied by x to the power minus n. And then using the first law gives you x to the power m plus minus n, which equals x to the power m minus n, which is the second law.